This is 5.1.3, resistivity. Now, resistivity is a property of a material. So it is a material property. And it determines the resistance of an object given its length and cross-sectional area. The equation for this is given by rho equals to R A over L. And you can also rearrange this to find R. So you could also say R equals to rho L over A. And we can define what these things mean. So rho is resistivity, which has units ohms, meters, not ohms per meter, but ohms, meters. R is resistance in ohms. A is the cross-sectional area. In meters squared. And L is the length in meters. Now, if you think of a simple wire and you zoom in onto it, you'd realize that a wire is, in fact, a three-dimensional object, as thin as it might look. And it does have a cross-sectional area. And the shape of a wire, a typical wire, is just that of the shape of a cylinder. Now, you could model wires as cuboids as well, extremely thin cuboids, if you've got a square cross-section. But for the most part, usually wires are modeled as cylinders. So let's say for a wire, we model them as a cylinder. So here's a cylinder. This here is the cross section. And then we have the length of the wire. Now the cross section is circular. Which means that it has a radius r, or you could even say that it has a diameter d. So if radius is known, then the area of the circle is given by pi r squared. And for diameter, you could either just work out that radius is half the diameter and then put it back into pi r squared, or you could remember another formula for the diameter. which is area equals to pi d squared over 4. So these formulas are actually the same. Now, if you had a different cross-section, then you just have to use whatever cross-section you got. So if it's a square, then you just work out the area of the square. If it was a rectangular cross-section, you work out for that. Sometimes they might even give you a novel material or a novel shape, I should say, rather than a novel shape, and get you to work out the resistance of that. So, for example, you might be given something like conducting putty. Now, conducting putty can be rolled into all different shapes. So you might do one calculation based on an original cylinder, then they might roll it into a different shape, they might flatten it into like a sheet, and then you might have to do the calculation again. Now, depending on the shape that's been rolled into, its resistance will change, but its resistivity will remain the same. Now, let's talk about different types of materials. So, we start off with conductors. Now, conductors have free electrons, which basically means that these free electrons are free to move from one atom to the other within the crystal lattice. Conductors typically have very, very low resistance. And this is something that you know from GCSE. But now you're also going to have a new type of material called semiconductors. Now, semiconductor materials behave differently to conductors. In a conductor, you only have one charge carrier. Those charge carriers are called electrons. So if charge were to move in a conductor, it's going to be electrons that move. In semiconductors, you have two types of charge carriers. So they have two types of charge carriers. So these charge carriers are electrons, which are negative, and holes, which are positive. Now, a hole is just a place in the semiconductor crystal where an electron could have existed but does not exist. And the electrons and holes can shift around and move around. So the gap where an electron could exist could move to somewhere else by an electron taking up that gap and creating a gap somewhere else. Now, in a conductor, if you heat the conductor, then the atoms vibrate with greater amplitude. We talked about this last lesson. If they vibrate with greater amplitude, it makes it more difficult for electrons to pass through. If it's difficult for electrons to pass through, then what happens is that the resistance has increased. Now, semiconductors don't behave the same way. In semiconductors, if we heat them up, or I could say if we provide them with energy, then the charge carriers, so for example electrons, can become excited into the conduction band where they can now conduct and behave like free electrons. And more of them become available to conduct. So, for semiconductors, providing energy e.g. heat, excites charge carriers to conduction band and decreases resistance. So the summary is, a conductor, e.g. a metal, has more resistance when it's hot. A semiconductor has more resistance when it's cold. Excites charge carriers to conduction band. Next, we'll briefly talk about insulators. Now, insulators have very high resistance because they have very few free electrons. Now, we'll talk about the next thing, which is superconductors. Now, if superconductors are cooled down to below something we call a critical temperature, then the vibrations of the atoms in the crystal lattice cease completely. The atoms stop vibrating at all. And when those atoms stop vibrating, then the resistance has become zero. And when resistance has become zero, when a current flows through that material, no work is done in that material. So you can have very, very large currents through a superconductor and not cause any heating, because the electrons can just flow freely without bumping into any atoms, without any energy losses caused by friction. So we can say materials become superconducting when their temperature is below their critical temperature. And typically, this is between minus 150 degrees C to minus 200 degrees C. So it depends on the material that you're working with. So these materials can be cooled using liquid nitrogen. Then liquid helium. So below the critical temperature, atoms in the lattice stop vibrating. Resistance becomes 0. And so very large currents can flow and no energy wasted. So what we mean by that is if we put one of the electrical equations in, if we've got P equals to I squared R, if R equals to 0, then P equals to 0. So the act of transmitting power through cables usually wastes some energy in the cables. Even if you don't notice any heating of wires, they are generating some small amount of heat all the time. Now the larger the current you try to transmit through a cable, the more energy it's going to lose to heat. So think about the national grid, for example. They use step-up transformers to step up the voltage and decrease the current to reduce heating effects in the transmission lines. But if you look at transmission lines, sometimes you'll see birds sitting on them. And they sit on them because it's warm, because they're losing energy. They're wasting some energy. With a superconductor, there is no energy lost in the cables at all. So one application of this is to make large electromagnetic coils for MRI machines. So those coils will then be able to handle extremely large currents. That causes extremely large magnetic fields that then can interact with the magnetic fields of the atoms in your body and the molecules in your body, and then allows you to image it.
Last equation, if R is equal to 0, doesn't P just equal to I squared?
Times 0.
Okay.
Anything times 0 is 0. So it's got applications in MRI machines, or magnetic levitation. Now we'll do temperature resistance relationship. And just to caveat this is for conductors. So I'm only talking about conductors here. So if we imagine atoms in a lattice with electrons flowing through. And we'll do a little key on the side where these circles are your atoms. And on just one of them, I will label the vibrational mode. And now I want to imagine all of the atoms vibrating according to those arrows I've drawn. If an electron now tries to pass through, so here's our electron trying to pass through. If it collides with some of those atoms during those vibrations, the electrons become deflected as they move along. And they do lose energy in that process. So, if the material's hotter, or I should say at higher temperatures, amplitude of vibration is greater. And resistance is greater. If we draw the same thing again, but this time it's superconducting, so when superconducting, amplitude is 0, which means there's 0 vibrations. And so our electron that wants to flow through can simply just flow through. When superconducting, amplitude is 0. At higher temperature, amplitude of vibration is greater, resistance is greater. So we can say here, 0 resistance and 0 energy lost. Now, anything in between superconducting and the initial stage, where we're decreasing the temperature, we're just decreasing the resistance, we're decreasing the energy losses. Once you've reached superconductor, if you carry on cooling it further, you're not going to gain any benefits after that because it's already superconducting. And that's the end of 5.1.3.